independence. So let's do that. And today we will try to apply, and this way you will see even the last day's questions will come to use. Yeah. Please note down all the small things I asked you to do. Then you will see that then integrate. So we will try, let's see, we'll try to apply the theory of matrices, matrices, row operations, and so on, matrices to vector spaces. So this you will maybe find interesting. Usually, I have discussed these things in the past with other people, and I have used other approaches, but all same. Right. So yeah, so V was a vector space. I hope the definition is now fine. F is the underlying field, and of course we have one operation which is addition, and one which is scalar multiplication, where this is coming from a field. This side by side, I would also like to develop this. If you so, well, one question: is it clear to both of you that V and this, if you forget this too, then V and this plus forms an abelian group?
Yes, sir.
Yes, sir. Commutative.
Perfect. All right. So that forms an abelian group. Right. And now I want to I'm just changing this V to M, nothing more, just because in the general theory it is like that. I can continue to use V. Just M. And this F will change by R. And R is a ring. So you can think of integers. Okay. And then again, some operation which is exactly like that. All the properties are true. And again, there is a scalar multiplication. Okay. So this thing is called a module. This will be very useful to understand linear transformations and so on. Module over ring. So it is just like a vector space, but there is a ring where scalar multiplication is happening by a ring and not by a field. Or module over the ring. So we can see to whatever extent we can carry forward the theory there, to some extent we will try. Right. So what is the key thing that we are trying to establish here? Trying to establish that there is a basis. Every vector space has a basis and with a unique cardinality. Basis is not unique, but cardinality is unique. So for that we had to
module over ring.
Mm-hmm.
Module over ring. What is it?
Right. So it is an abelian group M. M is an abelian group with addition. Okay. And there is a scalar multiplication which is given by the ring. I have not formally defined it. Right. This is it.
One single example that would be
right.
clear.
Yeah. The reason I'm not giving a definition is it will make it complicated, but just an example. So let's think of an example. Yeah. Why don't we give you an interesting example? So let's take R2 and let's take Z and the usual thing. So addition of vectors will be as it is, but this will be as it is. But multiplication will be by scalars, but only Z will be allowed. Is it fine? It is just
Which
like a
module over
sorry.
that's the whole module of ring, like for the R square Z plus minus.
Right. So R2 is the module and ring is Z. Vector space over field, and here we have module over ring.
Okay.
You may find this a little, but it's very, very useful. It will just come soon. I'm not giving the good example now because it will confuse you. So yeah, I'll just keep it. Right. Okay. So here it's clear, right? So I'm just repeating this in a slightly different way. So a module over a ring, the definition is that M plus this is an abelian group. Now the definition is coming. This is an abelian group, and there is a binary operation which is, or not a binary operation, but there is a function like this from R cross M to M. And what is this? It's just like in vector spaces for R and M respectively. This is again in M. Okay, with the usual properties, right? R of M, so it's just like vector space, and so on. R1 plus R2 times M. Okay. So it is like this, and right. It will be very useful when you come to eigenvalues, eigenvectors. Anyways, let's move forward. So have you checked minimal generating set is the same thing as a maximal independent set? All right. I will assume you have checked this. All right. Now tell me, what is the definition of a finite dimensional vector space?
A vector space which have a finite dimension of basis.
Without using basis, can you say? Without using the word basis?
So a vector space which has finite number of elements.
No, certainly it doesn't have finite elements. R2 doesn't have finite number of elements.
Yeah. So
Yeah, you're trying to say finite generating set maybe. Okay. So you want a definition that does not use basis, the word basis, but all the definitions is fine. So then let us not try to define it.
can we call it countably finite or uncountably? Sorry, uncountably.
No,
No, sorry.
that will not work. It can be anything. Let S be a let S be a minimal generating set. Let S be a minimal generating set. Let S prime be a generating set. So what should we try to prove? We will try to show that cardinality of S okay, and this is where we will try to use matrices. Assume that the cardinality is finite. Yeah. Our goal is to show that all minimal generating sets have the same size. That will follow from here, but first focus on this. Take a minute and think. Also true for free modules, but we can do that later. So how do you bring in matrices? This is a good lemma to show, right? Showing this is important because then you can replace, if you take S prime as a minimal generating set, then you will see that size of S is less than size of S prime. If you reverse the roles, you know, again, so you get equality. So this thing. So let us see. So if you take this element of S1, S1 prime, this is, so you can write this as a linear combination, right? So you write it using linear combination from S. So you have
It's in S dash, right?
right, and it can be written from S using linear combinations from S because
Yes.
so you do that and see what happens. And similarly,
So shouldn't it be 2C2N in the second one, last quotient?
yeah. Right? Our goal is to show that M is bigger than, this is a theorem, so it's slightly, but our goal is to show that M is at least N. Is this a good approach? No, right? Maybe we should swap
Maybe
the role.
with substitution method, I mean,
Uh-huh.
if we have more elements in S dash
Uh-huh.
and S have less elements, and we can show that some will be extra elements in S dash that could be written as S. So maybe S is mod of S is less than equal to S dash.
Yeah, but initially you are assuming, right, that it has more elements. Initially you are assuming that S parameter. That's not
That's also written right as be a minimal generating set. So S dash has at least one element more.
no, no. Think again, go back to the definition of minimal. I said this last time, right? That minimal doesn't mean size. Minimal is not about smallest size. That is not the definition of minimal, right? Definition of minimal is that it doesn't contain another generating set, right? Minimal generating means that if you take away something from S, take out some element of S, that will no longer be a generating set. Okay. So that is the definition of minimal. So I mean, eventually it is true what you're saying, but that is exactly the theorem. Then we'll be done if you say that. Then everything as the minimal has the same size. That is what we are trying to show. Okay. So I swapped the roles and now you see. Now we will try to show that M is less than N. So use the row reduce echelon for, right? That is the point here to be done. So think about it like this. Maybe that's better. Yeah, I'm trying to intentionally do like this so that you can relate to the previous things you've done. There are many ways these things can be proved. Just for the moment, if you see this, if you apply the row reduce echelon for, then what happens? If M is bigger than N, if M is bigger than N, then what happens? You can see it from many approaches, right? If M is bigger than N, then there will be a zero row in the end. That has to be. Do you see this? When you do row reduce echelon form,
Yes.
right? Yeah, because right. So it's because like every row can have at most one, right? So you look at the first row, it may have a one. I mean, every row has a one. That's the second row, it will have a one, right? And they are in different columns, mind you, right? So by the time you come to nth row, all the columns are used up. And so the other rows will have to be zero. I mean, some more rows can be zero, but at least after n, at least the n plus 1th row has to be zero. That is what the row reduced echelon for, whose proof comes from just elimination, Gaussian elimination. that basic algorithm tells you. In square steps, you will know this. So that is it. And this I had also given for homework. This implies that Ax equal to 0 will have a non-unique solution, infinity many solutions. Okay. Now, are we done? Yes. How are we done? Right? See, the point here is that if S1 to Sm is a minimal generating set, which means it's a maximal independent set. Okay. Then when you take the row operations that you're applying on the right side, you also apply them on the left side, right? You also apply them on the left side so that they say there is equality. So you observe this. The row operations that you apply on the right side, you also apply them on the left side so that you have equality at each stage. But when you apply row operations on this, means that what does it mean? It means you're taking combinations. So if you're taking this S1 up to Sm and you're applying row operations, so what does that mean? It means that you have S1 up to Sm, and whatever row operation you had, that basically is multiplying by a matrix, right? Correct? It's basically multiplying by a matrix. And what does that mean? That will give you columns. Right? So the first column, the first, that will again give you a column, right? And this will be a linear combination of the SMs. Correct? So let's take an example. Otherwise it's misleading. So let's take an example quickly. My point is, before I give you an example, my point is that from here, when you apply those operations on this side, which I will explain by example, what you get at each stage is also a maximal independent set. Right? It will remain independent because you're applying invertible operations. Okay? And so hence it will be minimal generating set. Okay. And then I rest. So then what happens? So assume that this remains the minimal generating set. So in the end, you get some very different vectors, W1 to Wn. This is a minimal generating set, and this is equal to this times this S1 up to S, right? Which means you will have an equation like this, but this will get replaced by W1, by W2, this will get replaced by W1, correct? Okay. But you will have a zero row, right? You will have a zero row, but that's not possible because this is non-zero. It's a non-zero vector, and this is a zero. That's the point. This row will become zero. So that's the point. So if you have to take example, so just give you a break, but first take this example, then you think. Suppose that there are two things here, okay, and here also, here let's say there are three things, okay. So you have S1 prime plus S2 prime plus S3 prime. And here you have S1 prime minus S2 prime plus 3S3 prime. Okay, writing it like this. And then if you apply an operation on this side, right, which means you just, I don't know, just do something. Yeah, whatever, right? So when you yeah, so when yeah, just you apply some operation, right? So you are 1 minute. So when you are multiplying, yeah, so when you are on this side and you are doing row operations, so you're basically taking linear combination of the rows, right? You're multiplying this row by something and this by something, and you're taking linear combinations. So you take the same linear combinations on this side also, right? So let's say you do S1 and you do S1 plus 2 times S2, right? So you are taking linear combinations of these things. You take this side also and you take this side also, the same thing. Okay? So, right. So you apply R1, replace R1 by R1 plus 2R2 on both the sides. Right? That's an invertible process, and therefore applying that on the S1, S2, the new thing you get, that will also be an independent set because you can go back. I will explain this after the break. The meeting is going to end. So that is basically your proof. But just in the break, think about it a little bit. Then we'll discuss. And this is not a trivial theorem. So it's, yeah.
But the vectors getting where W1, Wm, and Wm after the Wn term, they will, how can they will be zero? Vectors, they are non-zero, right?